Recording in progress. Oh, we're starting. Okay, the first question is, can you hear us? If you can hear us, let us know. Okay, exciting. Okay. Yes, yes, yes. That means yes. That's great. And oh, we got over 300 people here already. It's nice. Nice to see all of you. I have to apologize. So first of all, I'm Po-Shen Loh. Welcome to our live solve, and welcome to our YouTube channel. If you're on the YouTube right now, I have to apologize. I'm calling from a rather inconvenient location. I don't know if you can tell where this is, but anyone can guess? Yeah, actually, all three of us are roughly in the same part of the world right now. Yeah, that's an airport. I'm at JFK Airport, and I am joined by two awesome people. Eli is over in New Jersey, Arab is further on Long Island. And what we're going to do tonight is we're going to actually go over the AMC8 solutions. As far as I can tell, I don't think there's actually any large scale live stream of AMC8 solutions that I know of at all. So, well, I guess we're going to be the ones to take care of it. But just to make it more exciting, we actually haven't looked at the questions yet. This is on purpose. Some people have asked before, why don't you guys get more prepared? You should just go and look them up first. But then you wouldn't get to see how you actually get to solve the problems. So the good thing, though, is that there's three of us. And now the other two are Arab and Eli, and they have much better equipment than me because I'm stuck in an airport. So they will be doing the writing. They'll actually be going over the problems. I'll make commentary. But at this point, I think it'd be a good idea for them to introduce each other so you can know a little bit more about them. Arab, let me pop it over to you.
Yeah. Hey everyone, lovely to meet you all. And I'm gonna actually start off by talking about my good friend Eli. I'm gonna introduce him right here. So, Eli, he's a student at Princeton University right now, class of 29. He's studying math and music with also a minor in Chinese language. So he's pretty multifaceted. At the same time, regarding some math, he's a two-time USA Math Talent Search perfect scorer. So he's pretty good at this math stuff and really interested in it as well. Outside of our, math interests, he also is a world-class percussionist and marimba specialist. So he's really into the music. So that's really cool. And another thing, he loves combining math and music by practicing the English folk tradition of change ringing, which is ringing in mathematical permutations of tuned bells. I see some of his performances and I'm just stunned. So Eli's a pretty cool person.
Yeah, thank you so much, Arab, for that awesome introduction. And I think I might as well return the favor. So, who is this other co-teacher that I have named Arab? Well, he, on the math side, is a four-time AIME qualifier, loves all things competition math and problem solving. And even in addition to competition math, he's also done pure math research in combinatorial number theory, which is really, really amazing. And outside of math, he also has his own app that he's developed, which is really, really cool, called Halt Hate. So, you can check out that app if you want. All right, so awesome guy, Arab, that we have joining us. And I think with that said, we might as well start with the first
Good
question.
idea. Go for it.
Yeah, so AMC8 number one, we just have to evaluate this expression. Okay, well, sure, that's fine. Let's see. I think I can do this in my head. At least I'll try to. Okay, 1 plus 2 is 3, minus 3 is 0, plus 4 is 4, plus 5 is 9, minus 6 is 3, plus 7 is 10, plus 8 is 18, minus 9 is 9, plus 10 is 19, plus 11 is 30, minus 12 is 18. Okay. I don't feel like it's worth writing that out. I got A. Are we good? Let's see if it's
Yeah,
right.
I think that sounds right.
Awesome. It is the right answer. Cool. Back to you, Rob. Let's take it away with question two.
Yes. All right. So, question number 2. Here we see a array of numbers starting with threes in the center, going out to another kind of border of twos, and then ending with a border of ones. And we're asking what's the sum of all these numbers. So, it's not really different from the previous question. It's still just arithmetic, but here we just got to add them all up. I think the easiest way to do this would be to count how many threes there are, then twos, then ones, and multiply because it's repeated addition. So let's see. I think there's actually, the question says there's three threes, so they did that part for us. So 3 times 3. Then how many twos do we have? I think we'll have, we'll have 3 plus 3 plus 3 plus 3, or that should be put 12 twos. And the next border should be, I believe, maybe we can count them out. I think there's 20 ones because 20 ones. So that'll be 20 times 1, I think. Because if you have a 3 by 3 or a 3 by 5, it'll extend to a 5 by 7 in the perimeter, something like that. So if we add these up, we get 9, 24, 20, and putting those together, we should get a pretty nice 53. Choice C. All right, let's see if that's the correct answer there.
Ooh, I see that it is. Awesome job, Arav. Just some more computations that got us the right answer of 53. And, well, speaking of 3, here's question number 3. It's a long one. Okay, Haruki has a piece of wire that is 24 centimeters long. Okay, so it's a 24 centimeter piece of wire. Great. He wants to bend it to form each of the following shapes one at a time. Okay, a regular hexagon with side length 5. Okay, so that's like this kind of shape with side length 5. A square of area 36 meters squared. So that would mean it has side length 6. Okay. And a right triangle whose legs are 6 and 8 centimeters long. Okay, so this reminds me of a 6, 8, 10 right triangle. So we have something like this, 6, 8, and then 10. All right, which of the shapes can Haruki make? So this is, I think, just asking us to compute not surface area, what is it called? Perimeter, that's the word, perimeter of these shapes. And it's not so bad. If we have a hexagon that has 6 sides and side length of 5, that means that it's going to be 6 times 5 is 30 for the first one. And, well, that's bigger than 24, so I don't think we can make this regular hexagon. Okay, a square of area 36 centimeters squared. Well, the square root of 36 is 6, so that's why I said its side length is 6. And then we just do 6 times 4 is 24, so we have just enough to make that square, so I think we can do this one. And then there's a right triangle with 6, 8, and 10. Well, I know that the last one is 10 because it's a right triangle. You can use the Pythagorean theorem or just recognize that this is twice a 3, 4, 5 right triangle. If we add these up, it's 10 plus 6 plus 8 is exactly 24 as well, I think. So that would also be 24, and so we can also do this one, which means we can do the square and the right triangle, which is option D. Awesome. So let's see, is D the correct answer?
Yes, I believe it is. There we go. Nice. All right. I guess we can keep it moving to question number 4. All right. And let me know if you guys can see me on screen. Hopefully we can be seeing the question that we're answering right now, right? So in this question, we're following Brian's savings as it decreases by 20% in July and then increases in 50% in August. So first, we're looking at a 20% decrease, then a 50% increase. So if we just say his original amount is some S, it doesn't really matter, but we multiply the decrease of 20%, which is really just 80% of the previous amount, so 0.80, and then we do the increase by 50%, which is equivalent to multiplying by 1.5, because 150% is 1.50. So multiplying these out, we should get a nice and easy, actually I think 8 times 15 is 120, so it should be about 1.20 times S. So that's the factor. 1.20 is the same as 120% of the original savings, giving us choice E. So that's a way to do it with decimals. You could probably do it with fractions or your other favorite method of ratios, but we should get to the same answer of choice E. Let's see if that's correct.
Yeah, I think I got the same answer. And I also see people saying in chat that one other method is just to say, like, the savings are $100. So then decrease by 20%, you're left with $80. Now increase by 50%, well, half of 80 is 40. 80 plus 40 is 120. And so our answer is 120% of 100, which is 120. That's just a nice way of avoiding anything with decimal points. It's just kind of cool. And I think it is the right answer, which is nice. All right.
Awesome.
Question number 5. Casey went on a road trip that covered 100 miles, stopping only for a lunch break along the way. The trip took 3 hours in total, and her average speed while driving was 40 miles per hour. In minutes, how long was the lunch break? Okay. So 3 hours total. Average speed while driving was 40 miles per hour. Well, okay, if it's 100 miles and it's 40 miles per hour, then 100 over 40 would give us the number of hours. So that'd be 10 over 4 is 5 halves, okay, which is 3.5 hours.
Or 2.5.
2.5. Oh, yeah, that makes a lot more sense. I was thinking it took longer to drive than the whole trip. Okay, yeah, 2.5. There we go. 2.5 hours. And so, okay, I think this just means the lunch break was 30 minutes. I mean, is there anything I'm missing here? I don't think so. So, yeah, I mean,
Believe
the
so.
whole thing was 3 hours. 2.5 hours we're driving. That leaves 30 minutes, half an hour. Okay, let's see if B is the correct answer.
I believe it is. Looks
Oh, it
like
is. Nice.
there we go. All right. Wait, that's a pretty cool question. Just following somebody's lunch break, we get to see how long they took. All right. So now we're on to question number 6. And here we are looking at Peter in his rectangular field. Ooh, squared away by Peter's field. So Peter has this rectangular field with 10 by 8. We see that his border of blackberries that he can reach, which is shaded in orange, is 1 meter thick around the whole rectangular field. We're looking for the area of the field that is shaded. So we're actually looking for the shaded region. But in my head, I see a rectangle, a bigger rectangle, and a smaller rectangle. And I think that the smaller rectangle is probably easier to calculate, at least because I know the area of a rectangle. I don't really know the area of a border. So let's just do those two calculations and then we'll move from there. The bigger rectangle seems like it's 10 by 8. Those are given, so that should just be 10 times 8 is 80 meters squared. The smaller rectangle should be smaller dimensions by exactly 1, minus 1, minus 1 on both ends, so really minus 2 on each dimension. So 10 will become 8, and 8 will become 6. So it's shortening to 6 tall and 8 wide, giving us a 48. Actually, probably don't even need to multiply it out yet, but we'll just keep doing it. And okay, we have these areas, but we need to remember we're looking for the shaded area. This 48 is of the inner region, so that means the outer region is 80 minus 48, which is 32, not 22, 32 meters squared. So the fraction we're looking for is 32 out of 80, which equals, what is 32 out of 80? Well, if we divide by 8 should be, or I guess 16 we can even do. Divide by 16 gives a nice 2/5. 2/5 is the area that he can reach. So I guess we should probably check if that's correct. Let's see, I think the chat is indeed agreeing.
Yeah, I see a lot of agreement there, and wow, I see agreement on my screen as well. So it looks like we have the right answer of 2/5. Cool. On to the next problem, number 7. Mika would like to estimate how far she can ride a new model of electric bike on a fully charged battery. She completed 2 trips, totaling 40 miles. The first trip used half of the total battery power, while the second trip used 3/10 of the total battery power. How many miles can this electric bike go on a fully charged battery? Okay, so 2 trips were 40 miles, and well, we know how long each of the first trips were, or each of the trips were in terms of the battery power, so we can just add those up, right? We have 1/2 plus 3/10 is, well, this is like 5/10 plus 3/10 is 8/10, which is 4/5. So 4/5 of a battery gave us 40 miles. Okay, that's nice. So if I want to see how far a full battery would get us, I just have to solve for whatever this full battery would be. I called it x. Well, okay, I can divide both sides by 4, so I get a 10 over here, and then I can multiply by 5, and it looks like that distance would be 50 miles. Okay, so that seems to me that the answer should be C here. We can move 50 miles on this electric bike on a fully charged battery. We'll say, okay, electric bikes, I see them everywhere on campus here, and they're like so dangerous. Okay, it's like people are riding around on motorcycles, but like next to pedestrians. It's just crazy. So I highly do not recommend getting or using an electric bike, but like if you have to, now you know that they can go 50 miles, which is pretty cool. Okay, let's see, is this the right answer? Looks like it is. Nice.
Yes. Okay, yay. That's a pretty fun and maybe potentially dangerous question there, but hopefully question 8 might not be so dangerous because it seems we're now looking at a poll of poll of just people, and we're asking about mathematical problems. So here it seems they got a 74% response of yeses to a question. And we're wondering what's the fewest number of people who could have been asked the question, could have been surveyed? Well, this seems to be related to fractions and 74% being also literally percent, meaning per hundreds. So 74% equals 74 out of 100. This is one way to think of the survey fraction. We got 74 yeses out of 100 people. Or we could have had less people if we can still have a whole number at the top, because you can't have half a person or 0.237 of a person. You have to have whole numbers, so we gotta make sure we can cancel evenly. If we cancel, we can see the both top and bottom are even, so they can be split in half. I think it's 37, hopefully my arithmetic is good, out of 50, and that should be the lowest that we can do this in. So that means that the lowest or fewest number of people we could have surveyed is this 50, or choice D. Okay, I think, let's see if this is correct. We have the magic answer on screen. Yes, choice D, 50. Let's go.
Indeed.
Right?
Okay, so nice job there. I like that we've been getting a lot of nice normal numbers recently. All the answers have been like nice. Nothing weird
No.
like, I don't know,
This.
792 or something. Okay,
Oh, true.
question number 9. What is the value of this expression? It's a lot of square roots, but I don't think we have to worry. I think it's going to be okay. Okay, let's just take it one step at a time. I see a square root of 81, and that makes me happy because 81, that's 9 squared. Okay, that's great. So that's just 9. This I can just say is 9. And then we have a 16. So in total, this is a square root of 16 times 9. But actually, both of these are perfect squares again, right? 4 squared is 16, and 3 squared is 9. So we get 4 times 3, which is 12. That's on the top. Okay, and then flip the coin over. Now we have an 81 and a 16. But we've switched. Which one is in the nested square root and which one is in the normal square root? So here we have a 4, right? Because square root of 16 is 4. And then we have 81 times 4. And, well, 81 is 9 squared, that's said here, and 4 is 2 squared. So this bottom part is actually just 9 times 2. And, well, I guess I don't need to be calculating these, but yeah, it is 18. And so if we take this fraction, 12 over 18, we see that they're both divisible by 2, and we get, let's see, 6 over 9. Okay, well, they're also both divisible by 3, and we get 2 over 3. Yes. Okay, that looks like option B to me. Will it be option B? It will be. It was meant to be. Okay.
Yes, this is a pretty interesting question here. I think that it's, definitely scary to see the nested square roots, but we got through it. We got to see 2/3 as our answer here. So I think we can keep it pushing to question number 10. Question number 10 is on screen now, and we're okay. 5 runners, and they're in the grueling X marathon, and we get some information about their placements or finishing times relative to each other, but we're trying to see overall who finished fourth. So let's see. All right, fourth place should be, well, I guess the best way to maybe go about this is to just start writing out or visualizing the question, because I think fourth in a row might be a little easier than fourth in words. So let's just start with the first statement. Nico finished 11 minutes behind Pedro. So I guess if we imagine Pedro over here, then if this is the ranking, where this is the fastest, then Nico is behind Pedro by like 11 minutes. I guess that's the number line, 11 minutes. Olympia finished 2 minutes ahead of Melina. Okay, I don't have Olympia or Melina on screen, so I'm gonna just ignore that statement for 1 second. But I see the second statement, or this third statement really, the next one, says 3 minutes behind Pedro. Okay, I have Pedro on screen, so now I'm gonna get to put Olympia relative to Pedro. Olympia finished 3 minutes behind Pedro, so that's pretty close to Pedro, but still behind, so that should be Olympia. 3 minutes. Probably do a different color, but I did not. And actually, let's jump back to this statement here. Now with Melina, we know that Olympia finished a little faster than Melina, so Melina should be just behind Olympia. So that's 2 minutes. Okay. Finally, our last statement, which I think will finish us off because we'll get all 5 people in the row. Olympia finished 6 minutes ahead of Luke. All right, so Olympia over here, Luke, 6 minutes away, backwards. So I should, I guess I chose the same color. Olympia over here, going Luke, Luke, Luke. Oh, I think Luke's gonna be behind Melina because 6 minutes more than the 2. So get Luke. I think I've just noticed what the question is doing with the names. LMNOP, or actually it's not exactly LMNOP, but those are the letters that they've chosen. All right, so it seems in this ordering, where we have the times listed out relative to each other, Pedro came in first, OML, Luke for 4th place, just ahead of Nico, but we're interested in 4th place. The runner, I guess last place runner-up, is Luke, A. Okay, let's see if we did this ordering correctly. Blah, blah, dun, dun, dun. I believe so. Yeah, there we go. Choice A, Luke. All right.
Yeah, it's crazy that they chose LMNOP and then didn't have the order be LMNOP. That's just mean of them. But okay, now we have question number 11, and ooh, I already see that this is really interesting, and I don't see any LMNOPs around, so it's got to be good. Okay, squares of side length 1, 1, 2, 3, and 5 are arranged to form the rectangle shown below. Okay, so this is the 1, 1, 2, 3, 5. Great. Curve is drawn by inscribing a quarter circle in each square and joining the quarter circles in order from shortest to longest. What is the length of the curve? This is like very famous. It's known as the Fibonacci spiral. These numbers are the Fibonacci numbers. So this is kind of cool. I'm not sure. Maybe there's like a way to actually calculate the length of this in like its entirety, like if this were to go on forever. But we don't have to do that right now. We just have to calculate this little finite portion. So let's go ahead and do that. We have a side length of 5 here. And, okay, well, the length of an entire circle of radius 5 would be 2 pi r, right? 2 pi times the radius, which would be 10 pi. But this is just a quarter of that, right? This is just a quarter of 10 pi. And so we would get 10 pi divided by 4. And all the 2's cancel, and we get 5 pi over 2. Great. And then we do the same kind of thing with 3. And, okay, well, if this was 5 pi over 2, I think you can imagine that this will be 3 pi over 2. It's the same kind of thing. And then this will be 2 pi over 2, which is just pi. And then pi over 2 and pi over 2, which together make pi. So I believe this should be 1 plus 1 plus 3 halves plus 5 halves. And, okay, some mental arithmetic, or I'll write it out. If we put everything over 2, that's 2 plus 2 plus 3 plus 5, which, by the way, is like 1 plus 1 Well, actually, it's not the same, is it? Well, whatever. I was thinking it was like some Fibonacci thing going on. Maybe it is.
Ooh, I want to jump in. I want to jump in. There is a Fibonacci thing going on. Let me just jump in here. I've been in the whole thing the whole time, and I'm also going to jump in occasionally whenever there's someone who has a great idea. Eli is right, and I think it's easier to see it if you didn't write 2 plus 2. Your first two is actually a 1 plus 1. Is that right?
Yeah, yeah, that's right. Yeah.
So there's a really interesting thing that happens when you add consecutive Fibonacci numbers starting from the first one. Actually, keep Eli spotlighted because I can't write. I'm stuck in an airport. But I think Eli, if you look at what happens when you add consecutive Fibonacci numbers starting from the one, look for a pattern. You'll see something really interesting.
Yeah, yeah, yeah. So if we start like
I'll
1 plus
disappear now.
1 is 2, and then 1 plus 1 plus 2 is 4, which is related to 3 and 5 maybe. 1 plus 1 plus 2 plus 3, well, that would be 4 plus 3 is 7. I think the next Fibonacci number is 8, so that seems related. If we do the 7 plus 5, that's 12. The next Fibonacci number is 13, so that seems related. Maybe it's the next 2 over minus 1.
Yeah, I think that's right. I
Yeah,
think
so
that's right.
in our case here, it's 1, 1, 2, 3, 5, 8, 13. And so I believe this would be 12 because it's 13 minus 1. And so if this had gone on for a much longer amount of time, we wouldn't have had to add up all of the Fibonacci numbers. All we would have had to do is go 2 further and then subtracted 1. So it's a nice trick. We didn't really need it that much for this problem because this is not very hard to add, but it is very cool to see how we might have been able to do a much more challenging problem if it had a lot bigger numbers. Okay, so we have 12 pi then, or 12 over 2 pi, right? And so that looks like 6 pi to me. And that looks like option B. So let's see, is B the correct answer now? Hey, it is. Awesome what Fibonacci can do for us.
Yes, I really love Fibonacci. Actually, speaking of that, you know, you mentioned my combinatorial number theory research. It was actually on Fibonacci for one of my first years. I was just doing Fibonacci analogs of some theorems. Actually, we'll see a theorem, I think, maybe later on, but I don't know. That's for later. I think right now we have this very interesting diagram. Okay, we are having 6 circles where the numbers 1, or digits 1 to 6, are to be filled in with the constraint that circles that are adjacent, or the boxes in between 2 circles, should be summing, or sum to the number in the box. Alright, so we could go about this by just randomly placing numbers, but I think it might be easier to think for 1 second and see that there's a 4. Okay, the 4 looks like, well, what adds to a 4? We could do 2 plus 2, but actually we can't because it has to be exactly once. So the only sum is going to be 1 plus 3. And okay, so that means that one of these is 1 and one of them is 3. I'm personally tempted to put the 3 here because I see 5 and I just thinking about the Fibonacci 2 plus 3 is 5. But we might not necessarily know which way to go. But let's just try one out. I think we have limited to a pretty good amount. So if we put the 3 here, the 1 here, and then we can start filling out the rest. Alright, so like we said, 2 should go in here. Then 2, 8, that means that 6 needs to go into this spot. 6 and 10. Okay, 10 would have been another spot where we could see, okay, 10 is pretty large. We can't do 5 plus 5, so it has to be 6 plus 4. It works out nicely here that the 6 is on this side, so that means that there must be a 4 on this side. And finally, combining the two, actually, we probably could have skipped to this, but just to confirm that it all works. 9 minus 4 is the same as 6 minus 1, aka 5. So digit 5 should be the one in the top box. Let's see. I think it is indeed. So that's choice D. Blah. Choice D.
Awesome. Yes, it is indeed 5. I feel like I've seen a lot of 5s today. I don't know, it just keeps on popping up. But there's no 5 in this problem as far as I can see. Wow, that's actually very coincidental. There's not a single 5 on my screen right now. Okay, question number 13. The figure below shows a tiling of 1 by 1 unit squares. I guess that's what these things are. Each row of unit squares is shifted horizontally by a half unit relative to the row below it. So, or row above it. So You can see that here, like the midpoint of the previous one lines up with the new edge of the old one. A shaded square is drawn on top of the tiling. Each vertex of the shaded square is a vertex of one of the unit squares. Okay, so I can see those vertices here. In square units, what is the area of the shaded figure? Okay, let's see here. I think this is all just about finding the side length of this square. Yeah, I think there's not much else to do. So let's see. These are shifted horizontally by 1 unit, right? Yeah. So, or half a unit. Okay, so these are all 1 by 1 squares. This is 1/2, and this is 1. So I think we can just start making a triangle. This whole thing down here would be 3, because we've gone down 3 rows. That's 3 side lengths of 1. And then this would be, well, it's a half plus a half, so this would just be 1. That's pretty nice. Well, I see a right triangle. I see a 3 and a 1. Okay, well, 3 squared plus 1 squared is 9 plus 1, which is 10. And okay, that means this must be the square root of 10, but I actually didn't even really need that, because the area of the shaded square would just be the square of the side length, which is just 10. That's the square of the square root of 10. And so I believe the area should just be 10, and that is one of our options. Again, super nice. These problems just love giving us nice numbers. There's other options here that are terrible, but 10, I think, is going to be our answer. So, is it? Yes, it is, of course.
Yeah, that's really nice actually that they didn't even have us do like some fancy square root stuff that because the Pythagorean theorem kind of gives us the side length squared, we can just use it like that. All right, so that was question 13. Now on to 14. We have Jami picking 3 equally spaced integer numbers. Okay, that's pretty specific, so it's probably important. Equally spaced on the number line. Okay, so number line, I'm just going to immediately draw out a number line. And the sum of the first and second numbers, so if we have the numbers, or I guess I should write them as different letters. Sum of the first and second is 40, and the sum of the second and third is a 60. Okay. All right. Well, I think one way we can approach this is we know that they're equally spaced, so we can try and find the total distance, because it's actually pretty nice. If we do keep these letterings of x, y, and z for the numbers, where x is less than y is less than z, then we have x plus y is equal to 40, and y plus z is equal to 60. In other words, I'm just saying the first and second numbers and the second and third numbers. So if we subtract these two, well, we can cancel out the second number, and we're going to actually end up with, well, if we subtract the second one minus the first one, it should be a z minus x. And I'm kind of algebraic it up a little over much. We probably have done this a little more numerically, but we can just see a nice little pattern here where it's going to be z minus x, or the third number minus the last number, is 20. The 60 minus 40. Okay, if we have 20 as the total distance, and we know that they're equally spaced, that means that the distance between each of the numbers is 10. Okay, that was a pretty long-winded way to get to the equally spaced distance, but that should help us out because, well, now we can see what these numbers are. X plus y, if they are 10 away and they add up to 40, I think there's only one pair of numbers that do that. It should be 15 plus 25. Those are 10 away and they add up to 40. All right, and that means that the third number must be a nice 35. And to confirm, 25 and 35 do indeed add up to 60. So if we add these all together, we should get, well, we can actually use some of the numbers. 60 plus 15 gives us 75. Right, so 75 is the total sum of the 3 numbers. Let's see. I say that with a statement, but I should probably check. Yes, right.
Ooh, I want to jump in. I want to jump in. So, hi, I disappeared. I think this is great. I love your algebraic approach. It's always fun to have lots of different approaches. I have the benefit of not having to talk immediately because I just get to watch Arav and Eli go. And I'll tell you something I thought of when I saw your x and y adding to 40. I don't know if you guys saw, but a few years ago, I accidentally discovered some other way to teach how to solve quadratic equations. And the heart of the idea was whenever you have two numbers that add to something, it tells you what their average is. On your diagram, Arab, you can draw like,
Mm,
okay, I think Arab can finish it from here. Like, if you know those things and use all the equally spaced, I think you can get done real fast.
yes. So because we know what the oh, actually, I think I'm blanking, but
Okay, let me go. So
yeah,
the x and y add to 40. If x plus y adds to 40, what's the average of x and y?
20. Yes, there we go.
Now, if you draw down that number line, and then you can start filling it all up because you also know about the yz, and you know equally spaced.
Yes, yes. So because we know that, again, x plus y equaling 40, that means that the average of them, if we divide by 2, should be 20. That'll be right in the middle of x and y. And similarly with y and z, they're adding to 60. Half of that is 30, should be in the middle of y and z. And because everything's nice and equally spaced, half of the distance between x and y is fitting kind of in between the 20 and y, and half of the space is also fitting between y and 30. So that means that the distance between 20 and 30 is the same as the distances between x and y and z, 10. We get a lot of 10s. So we can use that in either way, but we get that the 25 for y, and then we can move on.
Yeah, cool. And just another comment there. It's like once you know the 20 and 30 are there, you know that y is halfway in between them. So you get y is 25. And I'll just share another random thing is like when you have three numbers that are equally spaced and you know the middle one, the sum is triple the middle one. So then you
Mm,
get to 75. But I do want to say, if someone says Poe comes with the good solutions, it's actually not true. It's just that there's a difference between being the backseat driver and being the one who's directly on the front. I'm sure that if it was the other way around, other people would have other comments. So I want to say, the people who are doing this live solve straight, it's pretty hard. And so they're coming up with great solutions. It's just occasionally I'll notice something like this and I'll toss it in. So well done. Yeah, I'll disappear
yes.
again. Yeah.
All right. Really fun question there with equally spaced integers. We might see something else with equally spaced, so maybe we'll be able to use some of this fun average stuff actually. So I guess we can keep it moving though to question 15, right?
Yes,
So,
so another amazing answer of 75. We just keep on getting nice answers. And number 15. Okay, Elijah has a large collection of identical wooden cubes, which are plain on four faces and shaded on two faces that share an edge. Okay, so something like this. Maybe there's the four that are unshaded over here, and then the two shaded ones there. He glues some cubes together, face to face. The figure below shows two cubes being glued together, leaving three shaded faces visible. Okay, so these three shaded faces. What is the fewest number of cubes that he could glue together to ensure that no shaded faces are visible, no matter how he rotates the figure? Okay, okay, so we want to get rid of all of the shaded faces using as few cubes as possible. This is pretty interesting. So in order to do this, we need to cover each of the shaded faces. And so we're going to at least need to have two cubes, right? We need to put one on here and one on here to get rid of those two. We're certainly not going to be able to get rid of two at once. So we definitely need at least three. Well, all the answer choices are bigger than four, so or at least four. So that doesn't really help. I guess we might have to just start thinking about it or in our heads or drawing it. This is going to be really terrible to draw. But let me see. Certainly we want to like put shaded faces to shaded faces because then we annihilate two and one. So we can do that twice, and then we seem to have. Oh, okay. I know exactly what to do. We only need four. I mean, it's the smallest answer. Yeah. So here's what we do. We have the okay. Here we go. The two shadeds are like this on one of them, and then we put the other two shades like this, and then like this, and then like this, and then they're all in the middle, and then they all just cancel each other out and can't be seen. Well, not cancel each other out, but they're all on the inside, so they can't be seen. I don't know if this diagram makes any sense, but it's like the shaded face here and here, like this, and then just kind of flip it and have the two shaded faces there and there. And then the same thing with these. And then once you do that, the two shaded faces that are still visible are here and here. And so you can get rid of both of those just by putting one more there. And so, okay, it's nice that it's the smallest answer choice, but it also makes sense that there's no way we could have done it with only 3, because we can cover like this one and then this one, and then there's going to definitely be at least even 2 shaded faces left that we still need to do. So we know that we need at least one more, but we can get by with 4 and we're good. So, okay, let's see. Is that the right answer? It is. Okay, nice.
Yeah, that's a pretty interesting question there. A couple of faces, but we got there in the end with 4. Pretty small, actually, so didn't have to take too many of his large collection. We didn't have to play around with too many, but all right. Now we are moving on to question number 16. All right. Question 16 is discussing all the 4-digit integers with only even digits. So we're limited to even digits. And we're asking what fraction of them are divisible by 4. Okay, so if they're all even digits, I think they're all going to be even. But divisible by 4 is slightly different. So we're probably going to need to just analyze it a little bit. Okay. Well, I think first we should write out the 4 digits. And because we're being told it's 4-digit integer, that means the first digit, the one in the front, can't be 0. We got to make sure it's either 2, 4, 6, or 8. But for the rest of them, we have some more freedom of choice. We have 0, 2, 4, 6, 8, and same for the rest. So if we do so like that, I guess I'll just write it out for fun's sake. 6, 8. So that means that how many, or what is the number of positive 4-digit integers consisting of only even digits? It should be, well, the first digit has 4 choices, the next one had 5, 5, and 5. I'm not going to multiply that out because we're going to get some nice cancellation. Because now we're trying to find out how many of them are divisible by 4. If you're familiar with divisible by 4, or even if not, well, divisibility by 4 is kind of like divisibility by 2, because an even number is divisible by 2, which is only dependent on its units digit. So you only have to look at the units digit to see if it's divisible by 2. For divisible by 4, you only have to look at the first 2 digits, because every 100 is divisible by 4. So we don't have to really worry about the choices for hundreds and thousands. So actually in our count, that'll look like 4. We still have 4 free choices and 5 free choices for these 2 digits, but we got to worry more about the first 2. Okay, for the first 2, well, let's see. If the tens digit is 0, what numbers could the units digit be? Well, if the tens digit is 0, we could have a 0, 4, or 8 as the units digit, because I know that 0, 4, 0, 8, or even 0, 0 are all 4-digit or 2-digit numbers that are divisible by 4. Similarly, actually, I think for if 2 is the tens digit, we'll also have 0, 4, 8, because I know that 20 and 24 and 28 are all still divisible by 4. And that should continue down. We'll get the same 048, 048, 048 for the rest of the tens digits. So that means that there's 3 choices of the units digit out of 5 possible choices for each one. So continuing with my kind of big fraction over here, we can say that that's still for any choice of tens digit. So for any choice of tens digit, we have exactly, oh, can't switch my color. We should have, I'll just keep the same color then, 3 choices for the units digit, because only these units digits will work. All right, I think we can cancel this out now. Like I said, I didn't want to multiply it out because we can cancel out basically everything. All of this, we just left with 3 over 5, which comes out to just 3/5, or choice D. I think that is the right answer. We can check it out really quickly. Yes, choice D, 3/5.
I want to jump in and say I got it wrong. So while you were doing this, so people have been saying like Professor Loh has such great ideas. So while Arav was going, Arav was like, okay, so they're all even, and so let's just figure out how many of them are divisible by four. And I was like, oh, duh, the answer's gonna be half. So this is the danger. So then Arav was doing all this, and I was like, Arav, why are you doing all this? It's gonna be half in the end, but it's not half. So you see, because I don't know if any of you were thinking the same way as I was, but I was like, all right, if it's divisible by four, but they're all even, then surely like half of them. So that answer C is so sneaky. But anyway, it was only until Arab did a couple of those that I was like, oh, all right. Anyway, good job, guys. I'm gonna disappear again.
Yeah, these questions can be pretty sneaky sometimes. I think that definitely the answer choices can trick you in, but for this one we got through it, figured out 3/5 is the actual answer for how many are divisible by 4. Okay.
Yes, it is. And it is I'd say, pretty unexpected answer, right? Because you just wouldn't expect a 5 to like appear in a question about fours and evenness. It's just kind of
Yeah.
interesting. But it just happens because there's like only 5 choices for even numbers. I missed 6. And then like only 3 of them work. So then, like for the last digit. So it's just kind of interesting. Okay, but we got the right answer. And now we're on to question number 17. We have 4 students seated in a row. They chat with the people sitting next to them, then rearrange themselves so that they are no longer seated next to any of the same people. Wow, they hated each other. Okay, how many arrangements are possible? This is great. Okay, so I'll just call them A, B, C, and D. And they rearrange themselves so that I guess A is not sitting next to B, and B is not sitting next to A or C, and similar like for all of these. I mean, actually, the only ones that actually matter are B and C, right? Because they determine everything else. So, okay. I mean, I was thinking we might just do like cases. I don't see a better way. And there's not that many. I mean, the biggest answer is 24. So well, of course it is. But there can't be that many. So I don't know if there's like a clever way, but I'm just gonna do this. So if B sits here, okay, A can't sit here, but it could be C or D. If C sits here, I'll just put out both cases. It could be like this. If
Ooh,
C sits here,
I'm just gonna jump in real quick. Is there a reason you didn't start with like the case where A goes first?
oh well, I guess I could do that. I was just doing cases based on where B was, because B gives more
Because B
information.
matters. I wanted to understand why you were doing it. Okay, smart. Go ahead.
Yeah, because B, I mean, gives more information. Like, oh, it can't sit next to C either. I mean, what am I even doing? I don't know. Yeah. So this was the reason I chose B, and then I didn't even use that information. So B can't sit next to A or C. Yeah, it's sit next to D. Great. So B to D, and then D. Now this is where we can actually have choices. So D just can't sit next to C. Oh, well, there's still no choices. It has to be A, and then after that, it has to be D. Okay, great. Then if B is here, it can't sit next to A or C, which I think just means this is impossible because,
You mean BDAC, by the way.
oh yeah, I do mean that. Yeah, okay.
Letters are always, it's the numbers and letters that when they're in a row, they always just get mixed up.
But this is actually kind of cool. Like B literally cannot sit back where they were because, I mean, there's only 3 more letters and there's 2 spaces next to them. So one of them is going to be A or C. So this is just impossible. Okay. And then the next case is here. And it's the same issue, right? If A or C is next to you, then you're dead, and that's the same problem. So the only other case is that B is on the end, and then we can just do the exact same thing in reverse, right? Then it has to be D, and then A, and then C. And so we get only 2 options, which is option A. Uh, Interesting. I mean, I was really hoping it would be option E, because that's the only letter that's not here, but oh well. We're going to get a double A, I guess. Let's see if 2 is the correct answer. And yeah, it is. Cool. Interesting how like those conditions were so stringent that it literally made it only possible to happen in 2 ways, and they were basically just the reverses of each other. That's kind of cool.
Yeah, I think it's especially because they were like in a row, so the B and C were the ones that had the most constraints because they were sitting next to the 2 people, which is what you started with, but it just makes it so much more constrained that they have to sit on the ends because the ends only have 1 sitting next to them. If this was in a circle, I think we would need more people to even have a possibility. Yeah, sometimes they change rows to circles. That's one extension to make harder questions. But for the next question that may or may not be harder. Let's see. It's about, ooh, okay. We might be able to use some averaging here just because it's about consecutive odd positive integers. So consecutive odd positive integers are skipping by 2, but they have to only skip by 2, really. And we're looking for when they sum to 60 and we have either 2 or more of these positive integers. Okay, so my first, go ahead at this would be, they say 2 or more, so I'm going to start with 2. I'm going to see if there's a way to do it with just 2. Well, if it's, actually, speaking of the averaging idea, I think it works really well here because 60, right, if we're trying to split it into 2 numbers, the 2 odd numbers that we choose, well, yeah, if we're splitting it into 2 numbers, we can consider the half of it, which is 30. And 30 is very nicely spaced from 2 odd numbers. It's 1 away from 29, and it's also 1 away from 31. And as it so happens, 29 and 31 are thus consecutive odd positive integers. So this is one valid combination. We have 29, 31 as a good tuple, I guess just pair here for this count. So that's 1. All right, now we gotta somehow keep going. But I noticed that when we did this, we kind of like divided by 2, so maybe we're gonna be constrained by how many factors that 60 has, but we'll just keep going. Okay, if we're going for, let's just try 3 consecutive odd numbers, I don't think that'll work, because if we have 3 consecutive odd numbers, maybe if we think about the number line actually, 3 consecutive odd numbers will be like this, where they're equally spaced by 2. Actually, this is really similar to the question before with XYZ or the skipping by 10, but here we're skipping by 2. Well, the average of all of them will be the middle number, the middle odd number, and like Professor Loh had said, the sum of all 3 will be 3 times the middle number, and 3 times the middle number equaling 20, that means that the middle number would have to, alright, sorry, I just said the answer, but 3 times the middle number equaling 60 means that the middle number would have to be 20, and 20 is not odd, so 3 is not going to work. Alright, that was some work to look at 3, but maybe that'll help us out to speed up the rest of the process. So 3 doesn't work. I'll just move that to the side so we can refer back to it, but I'll note down 3 didn't work. Okay, I guess one thing to note was that 3 is an odd number of numbers and 20 was even. So that's probably why it didn't work, because it would have to be an odd kind of result from dividing that we get. But okay, let's try 4 numbers. Let's just keep it pushing. I think with 4 numbers, well, okay, we're going to get the same thing but kind of in reverse with parity. So 60 divided by 4 is 15 now. So we're saying that in our number line of the 4 averages, or that's not too equally spaced, there we go. We're saying the middle, which is kind of in between the 4 consecutive odd numbers, well, that would have to be 15. And if you're just in between 2 odd numbers, well, in between every 2 odd numbers is an even number, and 15 is not even, so that means that this is impossible, because we'd have to be doing with even numbers, so 4 doesn't work either. Okay, I think we're eliminating a couple of factors pretty quickly here, actually, because now we can move on to 5 numbers. I'll just keep it in the side, maybe I can bring it up later as well, but okay. 5. For 5 numbers, 60 divided by 5 is 12. That's the same issue as here. 60 is 5. Okay, so I'll just write it. 5 5 numbers with an average of 12. That's the same as like 3 with 20, where it was an even middle. So even middle is not good for an odd number of numbers. So 5 isn't going to work either. Okay, almost lastly, I think 6. 6, okay, this one we got to be careful with. 6 numbers. let's see. If we have 6 numbers, dividing by 60 by 6 will be 10. So that means that in our number line, we're having 1, 2, 3, 4, 5, 6. We're saying the middle guy there is 10. That should work because we're saying we want odd numbers at the ticks. So odd numbers at the ticks would be like 9 and so I'll go from the beginning. 5, 7, 9, and at the other end we're gonna have 11, 13, 15, which nicely go around 10. You can see this kind of smiley faces, rainbow. 9 plus 11 is 20, 7 plus 13 is 20, and 5 plus 15 is another 20. That gives a total of 60, and it worked out. So 60 works. All right, so that's 2, I guess, tuples or cases where we've gotten consecutive odd positive integers adding up to 60. And I think that's all of them. The last one that we would really need to check is 10 because, well, 8 wouldn't evenly divide, and actually I guess that might actually help.
Ooh, I want to jump in because I think I see a lot of stuff that you've done, and you're the backseat driver, which is called me, is just observing. And so this is great because what I observed you just do, JetBlue is boarding. One moment, please. Sorry about the background noise, but come on, guys. You're done talking, aren't you? Okay, here we go.
Never mind.
All right, here we go. So I've noticed that there's like this is an airport. They're boarding planes to Paris. They're boarding planes to everywhere. But yeah, okay, let's continue. So I've noticed you noticed something which is like every time you try to divide by an odd number, your 60 divided by an odd number is even, and that's how you know that the odd factors of 60 won't work. Like that, I think that's really powerful because like every time you divide 60 by the odd number, you're like, okay, then the middle number's got to be this even number. Oops, but the middle number is supposed to be odd because they're all odd numbers. Okay, so that's not going to work. And then I also noticed that when you were dividing by the even numbers, when you divided 60 by 2, see, if you have an even number of numbers, you want the middle thing to be odd. Wait, did I do that right? No, you want the middle thing to be even. Yeah,
Even.
if an even number of things, you want the middle one to be even. So that's why 60 over 2 was good. 60 over 4 is bad because 60 over 4 is going to give you an odd. So you actually need the only things you can divide by are the factors of 60, which have exactly 1, 2 in them. Because you can't have an odd, you can't divide by an odd, and you can't divide by 4, or else there's no more 2's. But then I also got it wrong because as I was doing this with the backseat driver, I was like, then the answer is clearly just the number of factors of 60, which have exactly 1, 2 in them. And that's wrong because you have to be positive. So you still have to go and check all of the cases. But there are only 4 cases, I think. I'm going to disappear again.
Yes, yeah, that's actually a really good point because the positive adds an extra constraint. I think if we were to just consider, without the positive part, it would be 4. But because, actually, we'll check it out right now. If we had 10 numbers and we were considering 10 consecutive integers, well, this might work, but the center would have to be 6, and then we'd have to have 5 numbers before that, and that's going into negatives. So that's too far. That's into negatives. We want positives, so 10 won't work. And just to be completionist, the 30 that would be on the end would also similarly not work because that would be way into negatives. So the only 2 cases that worked were the 6 and the 2, which gives us 2 ways for this to occur, aka choice B. All right. This was a doozy of a question, but we got to tie in some interesting concepts from even previous questions that might have hastened our process. And yes, we got choice B. All right.
All right, awesome marathon of a question there, but we got like the same answer that we got before for that other counting question. It's always 2, it seems. Okay, now it's question number 19. Miguel is walking with his dog Luna, a cat. When they reach the entrance to a park, Miguel throws a ball straight ahead and continues to walk at a steady pace. Okay, so Miguel is walking and also throws a ball, but keeps on walking, and then Luna runs ahead of him to the ball, which stops at a tree. And as soon as the dog reaches the ball, She brings it back to Miguel. Luna runs 5 times faster than Miguel walks. What fraction of the distance between the entrance and the tree does Miguel cover by the time Luna brings in the ball? Okay, we need to draw a picture here. So we have Miguel and then Luna, and they're starting in the same place, right? Miguel and Luna, but Miguel starts walking forward. Well, first Miguel throws a ball to a tree. Well, doesn't hit, well, not to the tree, but throws a ball and it ends at a tree. So that's here. And they're both walking, but Luna's walking 5 times as fast and then walks back. So, yeah, okay, let's say that Miguel is walking at like 1 meter per second, and Luna then would be at 5 meters per second or something like this. Um, this is so weird. Okay, so I guess we also need to know what distance this is, but I guess we can also just call this something, and then it wouldn't matter. Maybe,
Yeah, I
yeah,
think a
let's
good
just
number
say
might be 5.
5.
Like
I don't
5.
know. I was going to go with 10 for some reason.
Oh,
Maybe it
either
doesn't
way.
matter. But
Yeah,
I'm just
fine.
going to say it's 10.
Yeah, 10 is probably more even.
Okay, so let's say it's 10. So Luna runs to the tree, and that takes 2 seconds. I don't know why I wanted it to be 2 seconds, but yeah, okay. So then Miguel has moved 2 meters over. So this is 2. And then after that, okay, this is like I like thinking about these like 2 people are painting a house at the same time. Okay, because they're like both trying to fill in this space, and they're like working together, you know. So one of them is moving at 1 meter per second, the other is moving at 5 meters per second. So together they're moving at 6 meters per second to fill in a space of 8. Okay, so this is 8, and so if it's 8, then you just divide this by 6 to get the amount of time. So this would be 4/3. So it's 4/3 of a second. So that means that the distance Miguel has walked is an extra 4/3. Okay, and that's when Luna comes back. So it would be in total 2 plus 4/3 is the distance here, and then you just divide this by 10, right? Because it's the fraction of the distance between the entrance and the tree. So I believe it should be 2 plus 4/3 divided by 10. Okay, so let's see, what is that? That's 6 plus 4, which is 10 over 3. Oh, divided by 10. Wow, that's nice. That's 1/3. And we get option D. That's really cool. I just like thinking about these things. I don't know why, but just the fact that, like, say if you have like cars on a racetrack and they're like running towards each other and they're about to crash into each other, you can just like imagine that they have paint on their wheels and like painting the racetrack. So they're like working together to do that. I don't know why, but I find that really cool because there are some problems that you learn about that are like, you know, people painting a house and then you have to work together to paint the house. And then whichever problem you find easier to solve, be it the cars crashing into each other or the people painting a house, you can just like switch between them and then think about it in a different way to solve it. And I don't know. I remember at one time in my life thinking about 2 people painting a house at the same time was really confusing. But maybe now that makes more sense to me than 2 cars crashing into each other. I don't know. So anyway, I believe we have option D. Maybe Po has something to say?
Yeah, I just wanted to toss in an idea. So yeah, you're right. Don't crash cars into each other. Don't try that. Huh? But like another thing, again, I can't draw, but like I'll make some hand motions. So if you imagine like the slow person is doing this while the dog is this one, they're doing this, which means that they combined cover double the distance. I'm doing it with no units. So I'm just like, like there's this distance here, and one of them is going this much, and the other one's going this much. So I'm just like, this distance, which is like double the distance, is split between this bit and this bit. But because one goes 5 times as fast as the other, this bit is 5 times as long as this bit, which actually gives you 1/3 in another way. I don't know if this made sense. Well, the good thing is that Eli can draw stuff, and it probably makes sense to him. Yeah, that's like 5 units and 1 unit.
Okay. Yes, I believe so. Okay, so the distance traveled by the dog is 5 times as much as the distance traveled by the person, and the total distance that they travel is twice of the 10 or whatever. I guess this would be like of the 6 or something. Oh no. Okay, because this is 1 unit. This is 5 units. Oh my god. Okay, I'm getting so confused.
I'm just
Uh,
doing it with no units. I, I'm trying to describe it with no units. I'm trying to be like if I had no units and I was just imagining like the dog ran along a string, like a string like this, and the person ran along a string like this. The person's string is 1/5 as long as the dog's string. So the two strings you have are like that. But if you try to put them together, then you have like 5 + 1 is 6. But they double loop it, which is why you got like this 1 + 5 is 6 altogether, if that made any sense. If you imagine like you had a string of length 1 and a string of length 5, and you put them together, and then you flattened it out.
Yes, okay. So the total distance traveled by both is exactly double the length of the track or whatever that they're going on. 1 + 5 is 6. You divide that by 2 to get 3 is the length of the whole thing. And the person walked 1, so it's 1/3. Okay, that's really cool. Yeah.
Well,
So
you're nothing wrong with your way, but that's just another thing. Okay, I'm gonna switch to phone because my plane's got everyone boarded now. But I'm gonna continue on the plane. Okay, so you just see me up here on a different device. But keep on going, guys. I'll be back.
all right, so let's
All
see if
right.
our 1/3 is the right answer. Hey, it's that's so
Ooh, that's a pretty interesting question there. Always the rates and stuff are always so interesting. Love that kind of way of both thinking of it with, choosing our own numbers or thinking without units. Both ways, especially helpful in this kind of case of trying to go quick. But here we're now moving to the land of Catania. Maybe that's where the two were running before. Here we have gold coins and silver coins, so those are our denominations, and we know that the gold coins are 1 millimeter thick and silver coins are 3 millimeters thick. Maybe I guess gold is more rare, so they want to conserve it and spread it out. Who knows? But the question is, how many ways can we get 8 millimeters tall of a stack using any arrangement of gold and silver coins, so any combination, assuming that the order does matter. Okay, so we actually do want to care about the order. Alright, so if we have some amount of gold coins and some amount of silver coins, well, we know that the total thicknesses should add up to 8 millimeters. So, I mean, my first guess for one way that we could make a stack is, let's say we use 8 gold coins. 8 gold coins, 8 millimeters thick. So if we do 8, I guess I can write it like this. So 8 gold coins, and if we, I guess we would have 0 silver coins in this case. Well, how many ways is there to arrange this? It's kind of boring. There's really only one way to arrange it because you can just stack all the golds. There's not really any switcheroos we can run. So that'll be 1. Alright, now we gotta think about what if we do have some silvers? Well, if we have 1 silver coin, that would take away our ability to have 3 of the gold coins in terms of thickness, because the thickness of 1 silver coin is 3, but the gold coin is just 1. So we gotta take away 3 of these to get 5, then we can have just 1 silver coin, but because the silver coin is that much thicker. Alright, now we have 5 gold, 1 silver, and the number of ways to stack that against each other would be kind of like a stack of plates, and we have like 1 special plate. And where can we put that 1 special silver plate? Well, there's 6 total spots, so any of those 6 spots, so that would be 6 different possible arrangements for that case. Alright, one more case. I think we have take away some gold coins to fit in another silver. If we take away another 3, that should be 2 and 2. Okay, so with 2 gold and 2 silver, now we can mix and match the golds and silvers a little more, and I think we'll actually get a pretty similar number to before, because now we basically have, alright, maybe I can draw it out a little bit. Blank, 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 and blank. I'm not sure of a very nice way to do this without, I guess I could do the counting here. So we have the 4 spots for the coins, and we're trying to look for, which two we can choose to be the golds, or which two we can be the silver. We can just choose two of them. So there's 4 choices for where we put the silver coin. Let's say we put the silver coin at the front. Okay. And then we have 3 more choices for where we put the other silver coin. Let's say we put it over here. Then the other 2 spots go to the gold. All right. So that was 4 choices. I guess I should write in the same color. 4 choices times 3 choices. But we should divide by 2 because there wasn't anything differentiating the silver coins. There was only between gold and silver. So it didn't matter which coin came first. This is something called like choosing, like 4 choose 2 or counting. Maybe you've heard it in that terminology, or we can just think through it and count it like that. So that should be, well, if we evaluate this out, 4 divided by 2, 2 times 3, 6. All right. 1 plus 6 plus 6 is 13 total here. Okay, I think that means that there's 13 arrangements with this currency and forms of denominations. So choice D, C, is it choice D? Am I getting that a good number? Oh, choice D? Yeah, there we go. 13 possible denominations. All right.
All right. Nice job. We got the right answer yet again. And I must say, I'm very sad that that wasn't my question to do because my last name is Gold. So I think it was like written for me. But okay, it's all right. Here we go. Charlotte is a spider. This is question number 21. Of course, Charlotte's Web, great book, walking down a web shaped like a 5-pointed star, shown in the figure below. The web has 5 outer points and 5 inner points. Great. Each time Charlotte reaches a point, she randomly chooses a neighboring point and moves to that point. Wow, okay, interesting choice, Charlotte. Charlotte starts at one of the outer points and makes 3 moves. Revisiting points is allowed. What is the probability that she is now at one of the outer points of the star? Okay, great. So starts at an outer point, right? So starts like, I'll make it green, over here. This is Charlotte now. And then just makes 3 moves. I think there's no difference between these 2 moves. So let's just say Charlotte moves here. I don't really care if she moved here because like I just rotate the diagram and it's the same. So, okay, now Charlotte makes 2 more moves. And is there like a better way? Maybe I might just like chart out each of these moves. Like, okay, on the 3rd move, either Charlotte moves to an inner point or an outer point. So let's just say first that Charlotte moves to an inner point. Well, that happens with probability 1/2. At this point, 2/3. Oh wait. Oh, she can revisit points. So it's not 1/2. It's not 1/2. Here we go. So at this point, going from here, actually, she could go to here or here or here or here. It is 1/2, but I was lucky. Okay, it's 1/2, but not because of what I said. So either inner points or outer points. There are 2 outer points and 2 inner points. So it's 1/2 probability that she ends up at an inner point. And if that's the case, then okay, there's 4 spots again, but actually exactly 2 of them result in being at an outer point. So it's again 1/2 to get the probability that she ends up at an outer point in that case. And then in the other case, it's again 1/2, right, that she ends up at an outer point. And from here, there's actually like nothing that can happen because no matter what Charlotte does, she'll end up at an inner point. So it's basically 1/2 times 0 because there's no way that she can get back to an outer point if she does this. So I think it's just 0 in that case and 1/4 in the other case, leaves us with option B. All right, I don't know if there's like a better way to do that, but I thought that was pretty efficient. Let's see if option B is the right answer. Hey, it is. Cool. All
Yeah,
right, back
that's
to
a
you.
pretty interesting question there with the kind of inner tracks and outer tracks for the points. Pretty fun to follow Charlotte on her journey there. But now we're following integers. It's not as I guess personified as Charlotte, but now we're thinking about medians. So hopefully we can think about what a median is. A median is the middle of a list, and in this case we're thinking about groups of 5. At first we're thinking about just 5 numbers, and then we have to think about, well, if we take the medians of those groups, so I'll just say like if the first group, second group, third group, fourth group, fifth group, let's say the medians of each of those are A, B, C, D, E. Then we're taking the median of this list. So if it was in this order, then C would be the median of that. So we're looking for the median of medians. And we're trying to say what the minimal value of this median of medians could be. I'm going to say medians, I guess count how many times I say medians, and that'll be a lot of times. But I think the first way we should think about this is, what does it mean to be a median of a 5-number list? The first kind of separation. If you're the median of a 5-number list, that means that you're having 5 numbers in a row, and you're in the middle, which means that there are 2 numbers kind of less than you, or, and very similarly, including you, there's kind of 3 numbers. We can think about this either way, but I think I can think about the 3 numbers. So if we have 3 numbers which are less than or equal to you as the median, well, that's a thing we should note, that we have 3 numbers less than or equal to you as A, and with B, and with C, and with D, and with E. These are the medians. Each of them will have 3 numbers less than or equal to it. But specifically, we're really focused on the first 3, because we're really worried about the the smallest medians. So in these 3, we're saying that, well, if A has to have 3 numbers smaller than it, or less than or equal to it, B has to have 3 numbers less than or equal to it, and so does C. That means that less than or equal to the median of medians. Really, I should be saying that C is the M as they defined it, but yeah. There's 9 numbers that are less than or equal to the median of medians. If we're saying that there's 9, or less than or equal to, so M is greater than or equal to 9. And I see that 9 is listed as an answer choice, so I'm pretty confident that 9 is our answer. We probably should construct an example where this is true, and I think the example where this would happen would be something like 1, 2, 3, or I guess maybe dark blue isn't the move here. We all do white. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then go crazy with the rest of the numbers. But let's say that those are the 3 of the sets, then we're guaranteed to have the median of medians be actually this 9 over here. Because, like I was saying, we only care about the first 3 sets, really, and really what's inside of those sets, even the first 3 numbers. That kind of way, we get to 9 as our median of medians. Yeah, this is a interesting question. Can be pretty mind-boggling to think about the median of medians, but median. Okay, there we go. 5 more times for the counters out there. All right, I think we should probably check, though, that 9 is the actual answer. I believe so. Yes. A.
Nice.
Yay! Yay! Okay. I'm sorry, I'm on a plane now, and I don't have the power to even start like myself whenever I pop in. But yes, that was exactly what I just said as I was listening to you. Beautiful. I just wanted to quickly address people have asked me, where am I going? I'm just going home. I was just in New York for a day. But I'll be in California on Tuesday. Anyway, so keep on going. Good stuff. This was excellent.
Yes, we love traveling. So next question, I think I'll let Eli take it away.
Indeed. Okay, we have question number 23. Interesting diagram I see. Lakshmi has 5 round coins of diameter 4. So diameter 4, okay, before I get confused, that means radius 2. I'm going to make that mistake. So, okay, she arranges the coins in 2 rows on a tabletop, as shown, and wraps an elastic band tightly around them. In centimeters, what would be the length of the band? Okay, I think I already see like the trick here. The trick is that, okay, it goes around in a circle once. So like there's some weird stuff going on, but it doesn't really matter. It's just like one circle. And then the other stuff is straight lines. So yeah. And okay, is there a nicer way to get the straight lines? is there something interesting going on there? I don't know. Yeah, no, I think this is actually easy. This is like fine. I think you just have to find like these distances, the distances between all of these points here, and then add a circle, and then you're like done. Yeah. Okay. So this would be just see 2 plus 2 is 4, and then 4, and then 4, and then this is a bit more than 4. It's 8, right? 2 plus 4 plus 2. Okay, so that would be 4 plus 4 is 8, plus 4 is 12, plus 8 is 20. And then 20 plus a circle of radius 2 is pi. Oh, this is perimeter. It's not area, but okay, yeah. This is 2 pi times 2, which is 4 pi, so 20 plus 4 pi. And that looks like option C. So nice trick for this one. Basically, okay, if I didn't really explain it, I mean, like, it's going around a bit and a bit and a bit and a bit, but in total it's going around one circle. So like all of these little arcs are going to add up to a single circle, and then all of the other bits are just straight line segments, basically between the centers, just extrapolated out a bit. So yeah, even though that like things might be confusing as to where exactly those things start, and if you wanted to find the exact arc lengths of all of these, it would be kind of problematic. It doesn't really matter. You just add up kind of these distances between the centers, and then one big circle, which is just the same as one little circle, and you get 4 pi plus 20, which is option C. Okay, is that the right answer? It is. Oh, well, I mean, it says A, but yeah, that was C. Whatever. I'll just say that's C. Yeah, same answer anyway.
Yes. Yeah, this is a fun question. I always love when it's just a band running around and then the hint to the arcs is that it's a full circle. And I thought this one visual and I thought it was really cool. It was like you think about an ant kind of crawling along. And if you're just thinking about the circular parts, well the ant, it's starting in one direction, it's gonna turn a little bit, it's gonna go, it's gonna turn a little bit, it's gonna go, it's gonna turn a little bit, go, so hit another turn. Oh, it's facing the same direction. So the ant kind of went a whole 360, and because they all have the same radiuses, that's just a circle with radius 2. So that means that the arcs are just one full circle. So another way to say the same thing that Eli did with a nice little ant, because I don't know, I think we were talking about a spider before, but now we're thinking about ants. Could be the spider from before, but I actually think the next question is about neither of those. It's about factorials. Ooh, factorials. This is fun. Okay, so here we seem to be defining our own little definition. Superfactorial. They love to do this where they make their own definition. So here it's where we're taking the factorial of each of the numbers and multiplying it together. And instead of just finding the factors of 7 in a factorial, now it's in the superfactorial of 51. Okay. Well, 51 is kind of close to 49, so I'm tempted to see something there, but that's probably later. My first thought is, well, where do factors of 7 come up in this question? Well, 51 superfactorial, I guess I'll draw it out in their notations, little superscript exclamation mark. So this is the same as 51 factorial, 50 factorial, all the way 49 factorial, I'll write it out. 49 factorial, all the way down to 7 factorial, 6 factorial, 5 factorial, all the way down to 1 factorial. And I specifically included 7, 6, and 5 because we'll notice that if you're multiplying 6 factorial and 5 factorial, even down to 1 factorial, none of those have factors of 7 because you can only get a factor of 7 if you have a 7 beneath you with factorial. That's just because you're only multiplying the numbers less than or equal to you. So these aren't really too important. But what is important is then the 7 factorial and the 8 factorial as well that's kind of in front here as, you know, in this list that I haven't fully written out because that's a lot of numbers. But both of these have one factor of 7. So they both contribute one factor of 7. Because the 8 factorial is the same as 8 times 7 times. So we have a 7 there. And same with 9 factorial. Same with 10 factorial. All the way up to 13 factorial. So I'll see if I can write it over here. So 7, we're saying all the way up to 13. Each of these are contributing one factor of 7. All right, but now we're going to go up to 14 factorial. 14 factorial contributes 2 factors of 7 because it has 14 and 7. Same with 15 factorial, 16 factorial, all the way up to 20. They will all contribute 2 factors of 7. And I think we're going to see a pattern here where this will continue. So if we keep doing this, we should get up to, I guess I will stop at like 48. So I'm just going to go to, wait, what is the numbers here? Yes, 17, 21, multiples of 7, 28. I'm going off screen, I believe. But let's see. If we keep going, it should get up to like 6 factors, because 42 sounds right. Alright, that should be good. Okay. 21, probably won't write them all out. 34, 35 to 41, 41, or no, 42 to 48. Okay, so each of these are contributing in order of succession. I wrote 6 there. 3, 4, 5, and 6 factors of 7. Each of those numbers. All right, but now we're on like the last segment, 49, 50, and 51. And this is where it gets a little tricky because this is the parts where you see the numbers are pretty close to each other. That's because these last 3 numbers have some extra special numbers of 7. So let's count it. If we're just thinking about, well, we can think about them individually. So that's probably just the one way to go about it. But yeah, actually, let's do it like the nicer way. The 49, right? If we're just thinking about factors of 7, well, 49 will have 7 factors of 7. But 49 also has a square, so we're going to think about the 49's contribution in 1 second. But let's just hold off on that. 49, 50, and 51, each of these contribute 7 factors of 7. Oh, my light is kind of bothering us, but we'll cover it. So, each of those are contributing a factor of 7, but they also have 49 factorial, which 49 is 7 squared. So that means that we're getting an extra factor of 7, which, deal for our bargain here. So really, it's going to be kind of like, what, +1, I believe? Something like that. So we can just kind of multiply and then add these numbers together, and I think we're gonna get to a nice E71. Is that what we should get to? I believe. Okay, I think Eli has it on his screen as well, a little more neatly written out and added up, but we should get to 171 as our final answer for this question. Is that true?
Yes, it is. I can like show it if you want.
Yeah.
So yeah, it's exactly what you did, but I just wrote out the computation. So each of these, I wrote them down. I was like 7 to 13 give 7 sevens, and 14 to 20 give 14 sevens, and so on. You can factor out the 7, which you already did. It's 7 times 1 all the way up to 6, and then each of these give 8, as you said. So plus 3 times 8. There's a nice formula for this. It involves 6 and 7. Interesting. So it's 7 times 6 times 7 over 2 plus 24. That's 7 times 21 plus 24, which is 147 plus 24. Ends up being 171. The computation is not the interesting part. We end up with option E as our answer, and is correct, as we see. We have like 1 minute, so I guess I can try to look at this problem really quickly. I'm probably not going to solve it, but let's see. We have a hexagon, side lengths 2, 3, 1, 3, 2, as shown below, inscribed in an equilateral triangle. So this is just an example. We want to think about all equiangular hexagons with positive integer side lengths that can be inscribed in triangle ABC, which is a triangle with side length, let's see, 2 plus 2 plus 2 is side length 6. We want to know how many hexagons. This is like a really weird question because we're trying to find the number of this weird object that honestly like I would never even think that this kind of thing would even exist. So is there a diagram for this? Well, there's this. I mean, that already has one drawn on. Um, I guess it's like we kind of need to partition the sides. And I don't even think it really matters. Yeah, I guess it doesn't really matter. All that it matters is what we do on one side, and that pretty much determines everything else, or does it not? Well, okay, I'll try to do this
We used
quickly.
to
Here we
make
go.
a random, we can make a random suggestion. I wonder if we can do it based on which triangles you took out. Which triangle you cut out. The
Oh,
triangles you cut out are 1, 2, 3, maybe 4. I'm not sure. Sorry, they're doing a safety analysis.
okay. Uh, yeah, so I see what you're saying. You're trying to cut out triangles from this, like you see in the other diagram here, where they cut out a one by like a one equilateral, two equilateral, two equilateral. So, and it like that's all that really matters is what you cut out from each corner. So you can do like a one, one, and one. You could do well like any combination, I guess, like these. Um, can you do a three, three, and three? Well, no, because then you get something weird like this, and that's not really a yeah. So you can't do anything like that, but you can do every other combination. Oh well, you can never have two threes. You can't have two threes because then one of the sides goes missing. Yeah, yeah. Okay, so you
Yes.
can't have two threes, but everything else would work because, like, if you had a three and a two and a two or something, it would be like this, and that's fine. So, okay. And since rotation doesn't matter, all that really matter is which numbers we have. So it's like ones and twos. Uh, okay, if we just have ones and twos.
You can have 4 too, I think. I think 4, 1, 1.
Ah, okay, so we can also have fours. Yes, so we just need to make sure that every pair of numbers doesn't add to more than six. Okay, we can just like list this out. There may be an easy way, but like I'm just gonna list them. Okay, and we're gonna get to the answer within the next minute. Okay, so like 1, 1, 1, 1, 1, 2, 1, 2, 2, and 2, 2, 2. Those are all fine. That's if we just have ones and twos. If we add a three in there, we could have 1, 1, 3. If we can't have two threes, so we could have 1, 2, 3, which is fine. Is there a more systematic way of doing this? I guess I'm just saying if I have a one. So if I have only ones and twos, if I have only ones and threes, there's only one way. If I have only twos and threes, I could have 2, 2, 3, yeah. And then if I have 1, 2, and 3, there's only one way. So that's everything with twos, only ones, twos, and threes. If I have a 4, there's only one thing I can do because I can't have a 2, so I can have 1, 1, 4. And if I have a 5, that's just impossible. So I think I only get these 8. Is 8 even an answer? Yeah, it is, and it's the biggest answer, so it's perfect. Okay, let's see. Is E the right answer? A it is. We did it.
Yes.
Only 2 minutes over time.
Ooh.
We're basically on time, you know.
Yay. My God, you guys are great. I apologize. My sound's off a lot. Sorry. But I have to lock up now. So nice to see you all. If you like this way of learning, we have lots and lots of things on our YouTube channel and we've got classes. Come join us. See you later. Bye bye. We're taking off.
Bye, everyone. Thanks for
Bye.
coming.
Thanks, everyone.